Here is something that should stop you completely, not slow you down, not make you pause and think for a moment before moving on. Stop you completely. Because what you are about to hear is not a riddle, not a philosophical game, not a thought experiment designed to make introductory philosophy students feel clever. It is the most fundamental fact about reality that physics has ever been forced to confront, and after more than a century of trying, it remains entirely, stubbornly, humiliatingly unanswered. The universe should not exist. Not in the way that a species might have gone extinct before it evolved. Not in the way that a star might have failed to ignite. Not in the way that life on Earth might never have gotten started if conditions had been slightly different. The universe should not exist in the most absolute sense of that phrase. According to our best understanding of the laws of physics, the conditions that produced the universe should have produced nothing at all. The matter you are made of, the light coming through your window, the planet beneath your feet, the galaxy wheeling overhead on a clear night, every atom, every particle, every quantum field vibrating in every cubic centimeter of space from here to the farthest edge of what any telescope has ever seen. All of it, every last piece of it, should have been annihilated in the first fraction of a second after the Big Bang, canceled out by its mirror image, reduced to a sea of pure radiation, expanding forever through an empty, structureless void. Instead, you are here. You are here, reading this, made of atoms, sitting on a planet, inside a galaxy, inside a universe stuffed so incomprehensibly full of something that we have spent thousands of years cataloging just the surface layer of it. And the reason you are here instead of nothing is a discrepancy so small that it fits in a single sentence. For every 1 billion particles of antimatter that existed in the first moments after the Big Bang, there were 1 billion and 1 particles of matter. 1 extra particle per billion. That is the margin. That is the entirety of the reason the universe exists as a place containing things rather than as an expanding shell of radiation containing nothing. 1 part in a billion, and we have no idea why. That is not a rhetorical flourish. That is not an exaggeration for dramatic effect. Physicists genuinely do not know why matter and antimatter existed in unequal amounts. They do not know what mechanism produced that asymmetry. They do not know whether it was inevitable given the laws of physics, or whether it was, in some sense that we do not yet know how to make precise, an accident. The question of why the universe is made of something instead of nothing is not a gap in our knowledge waiting to be filled by the next generation of particle accelerators. It is a hole at the center of our understanding of reality itself. A place where the most successful physical theories we have ever constructed simply go quiet. If you're new here, welcome. Find somewhere comfortable. Settle in. Subscribe if you want to keep following threads like this one, because what we are about to trace together is not just a scientific mystery. It is the mystery underneath every other mystery. The question that, once you understand it fully, makes every other question about the universe feel like a footnote. This is the story of why there is something rather than nothing, told from the quantum scale to the cosmic, from the first microsecond of time to the present moment, with honesty about what we know, what we suspect, and what remains genuinely beyond our reach. Let us start somewhere familiar, not in the abstract, not in a physics textbook, in your kitchen. You have, at some point, watched a candle burn. You have watched the wax melt, the flame dance, the wick slowly shorten. You have watched, in other words, something become less of itself over time. The wax does not disappear. It converts. It transforms into carbon dioxide and water vapor and heat and light, dispersing into the room, becoming invisible, becoming part of the air. But the atoms that made up the wax are still there, somewhere. Nothing was destroyed. Nothing was created. The total inventory of matter in the room, counted at the level of atoms, is exactly the same before and after. The candle just rearranged itself into a form you can no longer see. This is such a deep intuition that it feels less like a physical law and more like common sense. Things do not appear from nowhere. Things do not vanish into nothing. Something always comes from something. The universe is, on this reading, a vast bookkeeping system where the total account never changes, only the distribution of what is in it. That intuition is almost exactly right. And the place where it breaks down slightly, the place where the almost comes in, is the place where the entire mystery of existence is hiding. The formal version of this intuition is called conservation of energy and conservation of mass. And for most of history, they were treated as two separate laws. You cannot create energy. You cannot destroy energy. You cannot create matter. You cannot destroy matter. These laws were confirmed in experiment after experiment across chemistry and physics throughout the 18th and 19th centuries. They seemed as solid as any fact science had ever established. Then, in 1905, Albert Einstein published a paper that was not primarily about mass or energy, but that contained, almost as a footnote, the most famous equation in the history of science. E equals mc squared. Energy equals mass times the speed of light squared. What this equation says, stripped of its mathematical clothing, is that mass and energy are not two different conserved quantities. They're the same conserved quantity expressed in different forms. Mass is concentrated, frozen energy. Energy is liberated, flowing mass. The two laws are one law, and the conversion rate between them is the speed of light squared, which is an enormous number, approximately 9 times 10 to the power of 16 in SI units, meaning that a tiny amount of mass corresponds to a staggering amount of energy. This matters for our story in a very specific and unsettling way, because the equation does not only say that mass can be converted into energy, it says that energy can be converted into mass. Given enough energy concentrated in a small enough region of space, you can create matter from nothing but light. Not metaphorically, literally. This process, called pair production, has been observed in laboratories around the world for decades. When a photon with sufficient energy encounters the electric field of an atomic nucleus, it can spontaneously transform into two particles, one electron and one positron. An electron is ordinary matter. A positron is its antimatter counterpart, identical in mass, opposite in electric charge. Energy in, matter out. From light, particles. From nothing but concentrated electromagnetic radiation, physical substance. This is where the story of existence begins to get genuinely strange. Because pair production does not produce matter alone. It produces matter and antimatter in exactly equal quantities every single time, without exception, in every experiment ever performed. One electron and one positron, always together, always equal. The universe, it seems, has a rule. You can make matter from energy, but you cannot make matter without simultaneously making an equal quantity of antimatter. Which means that if the Big Bang was a process that converted the energy of the initial state of a universe into particles, which is our best current understanding of what happened in the first fractions of a second, then it should have produced equal amounts of matter and antimatter. One particle of hydrogen for every particle of antihydrogen. One electron for every positron. Perfect balance. Perfect cancellation. And then, when matter and antimatter met, which they would have done immediately because they were created together in the same hot, dense early universe, they would have annihilated each other. Two particles becoming two photons. Physical substance dissolving back into light. If the creation was perfectly balanced, the annihilation would also be perfectly balanced, and the end result would be a universe containing no matter at all. Just an expanding sea of photons, growing cooler and more diffuse forever, in a universe where no atom, no molecule, no planet, no star, no observer would ever form. That is what the laws of physics, as we understand them, predict. And it is not what happened. Something broke the symmetry. Something in the first moments of the universe tipped the balance by 1 part in a billion. For every billion pairs that were created and annihilated, there was one leftover particle of matter, one survivor with no antimatter partner to cancel it out. And that residue, that 1 in a billion excess, is the entire material universe. Every star, every planet, every person, every thought that has ever been thought inside a biological brain. The margin of survival of matter over antimatter is the reason there is anything at all. and we do not know what caused it. To understand why the asymmetry is so puzzling, you need to understand what it means for matter and antimatter to be perfect opposites. Because in physics, the word opposite has a very specific and very deep meaning, and the opposition between matter and antimatter is not superficial. It is written into the mathematical foundations of the theory. Antimatter is not science fiction. It is not a hypothetical proposed for theoretical convenience. It is real. It has been produced in laboratories since the 1930s, and the first hint of its existence came not from experiment, but from mathematics. In 1928, a young British physicist named Paul Dirac was attempting to write a quantum mechanical equation for the electron that was consistent with special relativity. The equation that already existed, the Schrödinger equation, described the quantum behavior of electrons accurately at low velocities, but broke down when electrons moved close to the speed of light. Dirac wanted a version that worked relativistically. When he wrote it, the equation had 4 solutions instead of 2. 2 of them described ordinary electrons, one with spin up and one with spin down. The other 2 described something else. A particle with the same mass as the electron, but with opposite electric charge. A particle that had not yet been observed, that no experiment had ever produced, that no one had gone looking for, that fell out of the mathematics of combining quantum mechanics with special relativity as an unavoidable consequence. Dirac initially tried to interpret these extra solutions as protons, the only positively charged particles known at the time. But the mathematics would not cooperate. The mass came out wrong. The particle predicted by his equation had to have the same mass as the electron, not the mass of the proton, which is nearly 2,000 times heavier. Reluctantly, Dirac accepted what his equation was telling him. There existed, or should exist, a particle identical to the electron in every property except charge. The electron has negative charge. This particle would have positive charge. He called it the anti-electron. We now call it the positron. Carl Anderson discovered it experimentally in 1932, photographing its track in a cloud chamber as a cosmic ray shower passed through. The track curved in a magnetic field in exactly the direction expected for a positive charge, with exactly the curvature expected for the mass of an electron. Antimatter was real. The universe confirmed what the mathematics had predicted, and the implication was immediate and profound. If every particle has an antiparticle counterpart, then a universe created from pure energy should, by the logic of pair production, contain equal amounts of both. The universe should be symmetric between matter and antimatter. Now here's what makes the asymmetry so deeply troubling. The laws of physics, as far as anyone can tell, are almost perfectly symmetric between matter and antimatter. Almost. Not exactly. Almost. And the deviation from exact symmetry, the tiny crack in the mirror between matter and its opposite, is at the heart of why you exist. There is a principle in physics called CPT symmetry. C stands for charge conjugation, which means replacing every particle with its antiparticle. P stands for parity, which means reflecting the universe in a mirror, turning left into right and right into left. T stands for time reversal, which means running the laws of physics backwards in time. CPT symmetry says that if you do all 3 of these operations simultaneously, replacing all particles with antiparticles, reflecting everything in a mirror, and running time backwards, the laws of physics look exactly the same. CPT symmetry is believed to be an exact symmetry of nature. It is a consequence of the mathematical structure of relativistic quantum field theory that is extraordinarily difficult to violate without destroying the internal consistency of the theory. Every experiment ever performed is consistent with CPT symmetry, but the individual symmetries, C alone, P alone, T alone, and combinations of 2 of them, those can be and are violated. P symmetry was shown to be violated in 1956 in the famous experiment by Chien-Shiung Wu on the beta decay of cobalt-60. The universe does not look the same in a mirror. The weak nuclear force, which governs beta decay, distinguishes between left-handed and right-handed processes. CP symmetry, combining charge conjugation with parity, was believed to survive even after P was found to be violated, but in 1964, James Cronin and Val Fitch discovered that CP symmetry was also violated in the decay of particles called kaons. The universe does not look the same when you simultaneously replace particles with antiparticles and reflect everything in a mirror. CP violation is the technical name for the crack in the symmetry between matter and antimatter. It means that matter and antimatter do not behave in exactly the same way under the weak force. They decay at slightly different rates. They are produced in processes with slightly different probabilities. The asymmetry is real and it is measurable. But here's the problem. The amount of CP violation observed in the standard model of particle physics, the amount measured in kaons and in mesons, and in every other particle system where it has been looked for, is not nearly large enough to account for the observed asymmetry between matter and antimatter in the universe. Not by a factor of 2 or 10, by many orders of magnitude. The standard model's CP violation can produce an asymmetry. It produces one that is far, far too small to explain why there is something instead of nothing. The observed universe requires a matter-antimatter asymmetry of roughly 1 part in a billion. The standard model, with all its measured CP violation included, can only generate an asymmetry of something like 1 part in 10 billion billion. The gap between what the theory predicts and what the universe requires is 10 billion times. The standard model does not come close to explaining existence. Something is missing. Some source of CP violation, some mechanism for generating a matter-antimatter asymmetry, exists in nature that is not captured by any theory we currently have. And finding it is one of the deepest and most urgent problems in all of physics. In 1967, a Soviet physicist named Andrei Sakharov, who is perhaps better known as the father of the Soviet hydrogen bomb and later as one of the most prominent human rights activists of the 20th century, published a short paper that laid out the conditions under which a universe beginning with equal amounts of matter and antimatter could evolve into a universe dominated by matter. The paper was 3 pages long. Its consequences have organized much of theoretical cosmology and particle physics for more than half a century. Sakharov's insight was to ask not what happened, but what had to have happened. Given that we observe a matter-dominated universe, what conditions must have been satisfied in the early universe for this to have come about? He identified 3 necessary conditions, now known as the Sakharov conditions, and they are worth understanding in some detail because they serve as the organizing framework for every subsequent attempt to explain the matter-antimatter asymmetry. The first condition is baryon number violation. Baryons are particles made of 3 quarks, protons and neutrons being the most familiar examples. Baryon number is simply a count of the total number of baryons minus the total number of antibaryons in a system. In all known particle physics processes, baryon number is conserved. You cannot create a proton without simultaneously creating an antiproton. You cannot destroy a proton unless you also destroy an antibaryon. The total baryon number of any isolated system never changes. If this remains strictly true for all processes at all energies, then a universe that begins with equal amounts of matter and antimatter, with a total baryon number of 0, must end with a total baryon number of 0. No net matter can ever be produced. For a universe like ours to exist, baryon number must have been violated at some point in its early history. Some process must have occurred that created protons without simultaneously creating antiprotons, or destroyed antiprotons without simultaneously destroying protons. The standard model actually predicts that baryon number is violated at sufficiently high temperatures through exotic processes involving objects called sphalerons, which are unstable field configurations that can convert baryons into leptons and vice versa. At the temperatures of the very early universe, these processes would have been occurring constantly. So the first Sakharov condition is technically satisfied within the standard model, though the details of how and whether this generates enough asymmetry remain debated. The second condition is C and CP violation. As we have just seen, the laws of physics must not be perfectly symmetric between matter and antimatter. If they were, Any process that created an excess of matter would be exactly counterbalanced by an equally probable process creating an excess of antimatter. The net result would still be zero. You need the asymmetry in the laws themselves to drive an asymmetry in the outcome. We know C and CP are violated. We have measured the violation. The problem, as we have seen, is that the measured violation is not nearly large enough. The third condition is a departure from thermal equilibrium. In a system in perfect thermal equilibrium, where all processes and their reverse are occurring at exactly equal rates, the forward and reverse processes will always wash out any asymmetry that attempts to build up. For an imbalance to be preserved, the universe must have been passing through a state of thermal non-equilibrium, a period during which some processes were occurring much faster than their reverses, allowing an asymmetry to be created and then frozen in before it could be undone. This condition was met during phase transitions in the early universe, moments when the universe cooled rapidly through critical temperatures and the nature of particle physics changed, potentially allowing asymmetries to be generated and locked in faster than equilibrium could restore. All three conditions are necessary. None alone is sufficient. And the central problem is that the second condition, CP violation, appears to be satisfied in nature, but not to the required degree. The universe is telling us that something produced far more CP violation than the standard model can account for. Something beyond the standard model generated the asymmetry that made existence possible. That something is what physicists have been searching for since Sakharov wrote his 3 pages, and they have not found it yet. Before we follow the search for that missing physics, we need to spend some time in what sounds like the simplest possible place: empty space. Because one of the most unsettling discoveries of 20th century physics is that empty space is not empty. And the non-emptiness of empty space is directly connected to the question of why matter exists at all. Quantum mechanics, the theory that governs the behavior of particles at the smallest scales, contains within it a principle discovered by Werner Heisenberg in 1927 that is among the strangest facts ever established about nature. The Heisenberg uncertainty principle says that you cannot simultaneously know both the position and the momentum of a particle with arbitrary precision. The more precisely you know one, the less precisely you can know the other. This is not a limitation of measurement technology. It is not a statement about the clumsiness of our instruments. It is a fundamental feature of reality. Position and momentum do not simultaneously have precise values in the way that classical physics assumes. They are complementary quantities whose precise values are jointly undefined at the quantum level. There is a second form of the uncertainty principle that applies to energy and time. You cannot simultaneously know the energy of a system and the time at which it had that energy with arbitrary precision. Energy and time are conjugate variables in the same way that position and momentum are. And the consequence of this for empty space is extraordinary. A region of space that is truly empty, with zero particles and zero energy, would have a precisely defined energy of zero. But having a precisely defined energy at a precisely defined moment would violate the uncertainty principle. Nature does not permit this kind of precision. Instead, even in a perfect vacuum, even in a region of space containing no particles and no radiation, quantum fields are constantly fluctuating. Energy borrows itself into existence for brief moments and then repays the loan. Virtual particles, pairs of matter and antimatter, flicker into existence and annihilate each other on timescales so short that they can never be directly observed. These are not hypothetical. They are real, and they have measurable consequences. The Casimir effect, first predicted in 1948 and experimentally confirmed in 1997, demonstrates that two uncharged metal plates placed very close together in a vacuum experience a slight attractive force. The reason is that the quantum vacuum fluctuations between the plates are restricted because some wavelengths do not fit in the gap, while outside the plates all wavelengths are present. The difference in vacuum energy inside and outside the gap creates a pressure difference that pushes the plates together. The vacuum is pushing on the plates. The vacuum is doing physical work. The vacuum is not nothing. The Lamb shift, a tiny but measurable difference in the energy levels of the hydrogen atom that cannot be accounted for by ordinary quantum mechanics, but is precisely predicted by quantum electrodynamics, when vacuum fluctuations are included, provides another confirmation. The vacuum interacts with atoms. It modifies their energy levels. It is physically real. Now here is where this connects to the matter-antimatter question in a way that is both profound and deeply puzzling. The virtual particles that flicker in and out of existence in the quantum vacuum are created in matter-antimatter pairs, exactly as pair production requires. An electron and a positron appearing and disappearing. A quark and an antiquark. A proton and an antiproton. Equal amounts of matter and antimatter, created and annihilated, conserving all the relevant quantum numbers, balanced perfectly. So the vacuum, left to its own quantum mechanical devices, respects the matter-antimatter symmetry. Virtual particles appear in equal amounts. They annihilate in equal amounts. The books are balanced. The vacuum contributes no net matter to the universe, just endless flickering of perfectly canceled pairs, unless something intervened in the early universe to break that symmetry, unless some physical process occurred that was not perfectly balanced, that created slightly more matter than antimatter among the fluctuations, and that then froze in that asymmetry as the universe cooled, and the pairs could no longer annihilate each other because the temperature had dropped too low. The question is not whether the vacuum can generate asymmetry in principle. In perfect thermal equilibrium, it cannot. The question is what happened during the specific moments of departure from equilibrium in the early universe that allowed a tiny imbalance to accumulate and survive. To answer that, we need to go to the first fraction of a second. The history of the universe has a strange property. The earlier you go, the more compressed the timeline becomes, and the more physics changes. Most of the interesting physics in the first second of the universe happens in intervals of time so short that they make a millisecond look like an eternity. The entire story of how matter came to dominate antimatter was written in a duration shorter than the blink of an eye, at temperatures higher than any astrophysical object in the current universe, in conditions so extreme that the forces of nature themselves were different from what they are today. At a time of roughly 10 to the power of negative 36 seconds after the Big Bang, a period so brief that there is no everyday analogy that does it justice, the universe is believed to have undergone a period of extraordinary exponential expansion called inflation. The proposal, originally developed by Alan Guth in 1980 and refined by Andrei Linde, Alexei Starobinsky, and others, holds that the universe expanded by an enormous factor in a fantastically short time, driven by the energy of a field called the inflaton. The details of inflation and the precise nature of the inflaton field remain uncertain. But inflation solves several problems with the standard Big Bang model, including the extreme flatness and uniformity of the observable universe. And it has the additional consequence of amplifying quantum fluctuations in the inflaton field into the seeds of all large-scale structure, the tiny density variations that eventually became galaxies. What inflation also does, potentially, is set the stage for baryogenesis, the process by which the matter-antimatter asymmetry was generated. After inflation ended, the energy of the inflaton field had to be converted into particles, a process called reheating. The universe went from an exponentially expanding, cold, nearly empty state back to a hot, dense plasma of particles and antiparticles. And during reheating and the subsequent cooling, the conditions for baryogenesis were potentially created. Several mechanisms for baryogenesis have been proposed, and each of them represents a different answer to the question of why the universe contains matter. Electroweak baryogenesis is one of the most studied. It proposes that the asymmetry was generated during the electroweak phase transition, a moment when the universe cooled to a temperature of roughly 10 to the 15th Kelvin in the electroweak force, which at high temperatures is a single unified force, split into the electromagnetic force and the weak nuclear force. If this phase transition was strongly first order, meaning it occurred through the nucleation of bubbles of the new phase in the old, rather than as a smooth, continuous transition, then the bubble walls moving through the plasma could have created the thermal non-equilibrium required by Sakharov's third condition. And the CP violation associated with the Higgs field's behavior at the bubble walls could have generated a baryon asymmetry. The problem is that within the Standard Model, the electroweak phase transition is not strongly first-order. Measurements of the Higgs boson mass at the Large Hadron Collider have established that the Higgs mass is approximately 125 GeV, and at this mass, the electroweak transition is a smooth crossover rather than a sharp first-order transition. The bubble walls do not form. The non-equilibrium is not sharp enough. Electroweak baryogenesis, if it occurred, required either a Higgs mass significantly different from what was measured or additional fields and interactions beyond the Standard Model that could modify the nature of the transition. The Standard Model, as confirmed at the LHC, does not give you the electroweak baryogenesis you need. Leptogenesis is a different approach that has attracted significant theoretical interest. The idea, proposed by Masataka Fukujita and Tsutomu Yanagita in 1986, is that the asymmetry was not generated directly as a baryon asymmetry, but first as a lepton asymmetry, an excess of leptons, the family of particles that includes electrons and neutrinos over antileptons. This lepton asymmetry was then partially converted into a baryon asymmetry by the Sfalern processes, the baryon number violating processes predicted by the Standard Model at high temperatures. The source of the lepton asymmetry in leptogenesis is the decay of very heavy particles called right-handed neutrinos, which are predicted by certain extensions of the Standard Model but have not yet been directly observed. These hypothetical particles, with masses perhaps as large as 10 to the 15th GeV, enormously heavier than any particle produced at any existing accelerator, would have been produced in the hot early universe, and their CP-violating decays would have generated an asymmetry between leptons and antileptons. That asymmetry, once partially converted to baryons by sphalerons, could in principle account for the observed matter-antimatter ratio. Leptogenesis is theoretically attractive because it naturally incorporates the explanation for why ordinary neutrinos are so light through a mechanism called the seesaw mechanism, connecting the mystery of neutrino masses to the mystery of matter-antimatter asymmetry in a single theoretical framework. But the heavy right-handed neutrinos, if they exist, have masses far beyond the reach of any particle accelerator we could contemplate building in the foreseeable future. Testing leptogenesis directly may be beyond experimental reach for generations. What connects all these proposals, what they all share, is the need for physics beyond the Standard Model. More CP violation than the Standard Model contains. A more dramatic phase transition than the measured Higgs mass allows. New heavy particles with CP-violating interactions. The universe is telling us, through the simple fact of its own existence, that the Standard Model is incomplete, that there are particles and forces and interactions that we have not yet discovered that were operating in the first moments of time and that are responsible for the fact that there is something rather than nothing. Among all the particles in the Standard Model, the neutrino is the most mysterious, and its mysteries may be the most relevant to the question of existence. Neutrinos are among the most abundant particles in the universe. For every proton in the observable universe, there are roughly 1 billion neutrinos. They are produced in nuclear reactions, in radioactive decay, in supernova explosions, in the collisions of cosmic rays with the atmosphere. Right now, as you sit reading this, approximately 65 billion solar neutrinos are passing through every square centimeter of your body every second, streaming out from the nuclear reactions in the core of the Sun. You are being traversed continuously by a torrent of particles so weakly interacting that the entire Earth is nearly transparent to them. For most of the 20th century, neutrinos were believed to be massless. The Standard Model, in its original formulation, did not include masses for neutrinos. They were like photons, particles of light, particles that traveled at the speed of light and had no rest mass. This was a reasonable assumption, consistent with all observations up to the 1990s, because neutrino masses, if they existed, had to be extraordinarily small. In 1998, The Super Kamiokande experiment in Japan, a detector consisting of 50,000 tons of ultra-pure water lined with photomultiplier tubes buried deep underground to shield it from background radiation, made a measurement that changed the picture fundamentally. The experiment was studying neutrinos produced when cosmic rays hit the upper atmosphere, called atmospheric neutrinos, and comparing the number arriving from above with the number arriving from below, which had traveled through the entire Earth before reaching the detector. The numbers were different. Fewer neutrinos were arriving from below than from above, and the deficit depended on energy in a specific way. The explanation was neutrino oscillation. Neutrinos come in three types, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. If neutrinos have mass, and if the mass states are not identical to the flavor states, a neutrino created as one flavor can spontaneously transform into a different flavor as it propagates through space. The atmospheric neutrinos were changing flavor during their journey through the Earth, converting from muon neutrinos into tau neutrinos, and the detector, which was sensitive to muon neutrinos but not to tau neutrinos in that configuration, was not detecting the converted ones. Neutrino oscillation requires neutrinos to have mass. Not much mass, tiny mass, but non-zero. And non-zero neutrino mass is not predicted by the Standard Model in its original formulation. The discovery of neutrino oscillation and the confirmation of neutrino mass is the clearest established experimental evidence for physics beyond the Standard Model that we currently possess. The reason this matters for the matter-antimatter question is that massive neutrinos open a theoretical window. If neutrinos have mass, they might also have CP violation in their mixing. The way the three flavors of neutrinos mix with each other, described by a mathematical structure called the PMNS matrix, may contain a CP-violating phase, a parameter that causes neutrinos and antineutrinos to oscillate differently. If this phase is non-zero, neutrinos would behave differently from antineutrinos in a measurable way, and this difference could, in the context of leptogenesis, have been the source of the original asymmetry. Several experiments around the world are currently measuring the CP-violating phase in neutrino mixing with increasing precision. The T2K experiment in Japan sends a beam of muon neutrinos from a facility near Tokyo to the Super Kamiokande detector 300 kilometers away, comparing how many of them transform into electron neutrinos with how many muon antineutrinos transform into electron and neutrinos. Preliminary results from T2K suggested a preference for CP violation in neutrino mixing. NOVA, a similar experiment in the United States using a beam from Fermilab to a detector in northern Minnesota, has measured results that have some tension with the T2K results, leaving the current experimental picture somewhat ambiguous. The next generation of experiments, DUNE in the United States and Hyperkamiokande in Japan, are designed to measure the CP-violating phase with much higher precision. Whether or not leptogenesis is the correct explanation for the matter-antimatter asymmetry, the neutrino CP measurement matters profoundly. If CP violation in neutrino mixing is confirmed and measured precisely, it will be the first direct observation of a difference between the behavior of matter and antimatter beyond what the Standard Model predicts. It will be a crack in the mirror directly visible in the laboratory that points toward the physics responsible for existence. There is a complication in this story that is worth pausing on, because it reveals something important about how honest we need to be with ourselves regarding the depth of our ignorance. The matter-antimatter asymmetry problem is usually framed as a question about ordinary matter, the matter made of protons, neutrons, and electrons, the matter that makes up stars, planets, and people. And it is. The asymmetry we observe is an asymmetry in ordinary matter, called baryonic matter in the language of physics, baryons being the family of particles that includes protons and neutrons. But ordinary matter, the kind we can see, the kind that emits or absorbs light, accounts for only about 5% of the total energy content of the universe. The remaining 95% consists of dark matter, roughly 27% of the total, and dark energy, roughly 68%. Both of these are inferred from their gravitational effects. Dark matter was first proposed to explain why galaxies rotate too fast for their visible mass to hold them together, a discrepancy that Vera Rubin's observations in the 1960s and 1970s made undeniable. Dark energy was discovered in 1998 when two independent teams measuring the distances to supernova explosions found that the expansion of the universe is accelerating rather than slowing down, requiring a form of energy with negative pressure permeating all of space. Neither dark matter nor dark energy has been directly detected. We do not know what dark matter is made of. We do not know whether it has an antiparticle counterpart. We do not know whether there is an asymmetry between dark matter and dark antimatter analogous to the asymmetry between ordinary matter and antimatter. We do not know whether dark energy is a constant property of empty space, as it appears to be, or whether it is a dynamic field that has been changing over the history of the universe. What this means for the matter-antimatter asymmetry problem is that we are explaining the origin of 5% of the universe. The origin of the other 95% is a separate set of problems that we understand even less well. When we say we do not know why the universe contains something instead of nothing, we are speaking most precisely about ordinary matter. But the something that fills the universe is mostly dark, mostly unknown, and mostly unexplained at a level that goes even deeper than the matter-antimatter asymmetry. The universe is not just asking us one question. It is asking us at least three, and the question about ordinary matter, the one this documentary is primarily about, is the one where we have the most traction. The darkness behind it, the dark matter and dark energy that dominate the universe's content, are further questions still layered beneath the first one, suggesting that the full accounting of why there is something rather than nothing has chapters we have not yet even identified. To be clear, the asymmetry between ordinary matter and antimatter is established observationally beyond reasonable doubt. The universe contains vastly more matter than antimatter. This is confirmed by the cosmic microwave background, by the absence of gamma-ray annihilation signatures that would result from large regions of antimatter meeting matter, by the observed abundances of light elements produced in the first minutes of the universe through Big Bang nucleosynthesis, and by every direct measurement ever made. The fact of the asymmetry is not in question. The mechanism that produced it remains unknown, and the framework we have to search for that mechanism, the Sakharov conditions, the various baryogenesis scenarios, the neutrino mixing measurements, the searches for new CP-violating physics at particle accelerators, all of these represent our best current strategy for finding an answer. They are serious, rigorous, ongoing scientific programs. They have produced real knowledge and real constraints, but they have not yet produced the answer. Ubi Lichtahun, Part 9 Se Akir Tak, 6,000 words, same cinematic tone. There is a building on the outskirts of Geneva, Switzerland, that sits mostly underground, invisible from the surface except for a few squat concrete structures and a ring of access shafts marking where the tunnels below pass closest to the surface. Beneath the fields and farmhouses of the Franco-Swiss border, in a circular tunnel 27 kilometers in circumference buried between 50 and 175 meters underground, protons are accelerated to 99.9999991% of the speed of light, and then made to collide with each other at 4 points around the ring. The energy released in each collision is small by everyday standards, roughly equivalent to the kinetic energy of a flying mosquito, but concentrated into a space smaller than a proton by a factor of more than 1,000,000. At those concentrations, conditions briefly recreate temperatures and densities not seen since the first fractions of a second after the Big Bang. This is the Large Hadron Collider, and it is humanity's primary instrument for probing the physics of the early universe in a laboratory setting. It is the most complex machine ever built. The superconducting magnets that bend the proton beams around the circular path operate at temperatures colder than deep space, cooled by superfluid helium to 1.9 Kelvin, just above absolute zero. The detectors that record the particle collisions contain hundreds of millions of individual sensing elements, generate data at rates that would fill millions of DVDs per second, and require global computing grids spanning dozens of countries to process. The LHC's greatest confirmed discovery was the Higgs boson in 2012, the particle associated with the field that gives other particles their mass, the final missing piece of the Standard Model. But the Higgs discovery, while scientifically historic, also delivered a message that was difficult to hear. The Higgs boson's measured mass, approximately 125 billion electron volts, sits in a range that is deeply uncomfortable for the most popular theories of physics beyond the Standard Model. Supersymmetry, the theoretical framework that posits a supersymmetric partner particle for every known particle, and that would have provided both new sources of CP violation and a candidate for dark matter, predicted that some of its particles should have been visible at LHC energies if the theory was relevant to electroweak physics. They have not appeared. After more than a decade of running, the LHC has found the Higgs boson and has found nothing else new. This is not a catastrophe. Absence of evidence is not evidence of absence. And the LHC is currently undergoing an upgrade that will increase its collision energy and luminosity substantially, potentially opening windows into physics that have not yet been accessible. But it is a sobering result. The most powerful particle accelerator ever built, operating for over a decade, has so far found no direct evidence for the new physics that baryogenesis scenarios require. Other experiments are pursuing the asymmetry from different angles. The Bell 2 experiment at the KK Accelerator in Japan is designed specifically to study CP violation in the decays of particles called B mesons, heavy particles containing bottom quarks. B mesons are produced in large quantities at the electron-positron collider, and their decay patterns are exquisitely sensitive to CP violating effects. The original Bobber experiment at SLAC in California and the Bell experiment at KEK both confirmed CP violation in B meson decays in the early 2000s, consistent with the Standard Model's predictions. Bell 2 is collecting data at higher luminosity, searching for deviations from the Standard Model's predictions that would indicate new CP violating physics. Any such deviation would be a direct signal of the physics beyond the Standard Model that baryogenesis requires. The most promising near-term avenue may be the neutrino experiments. DUNE, the Deep Underground Neutrino Experiment, will send a beam of neutrinos from Fermilab in Illinois to a detector filled with 40,000 tons of liquid argon located in a mine in Lead, South Dakota, 1,300 kilometers away. Hyperchemiocandi in Japan, a successor to superchemiocandi with a detector volume more than 8 times larger, will study both atmospheric neutrinos and a beam from a facility on Japan's west coast. Both experiments are designed to measure the CP-violating phase in neutrino mixing with sufficient precision to determine definitively whether neutrinos and antineutrinos oscillate differently, and by how much. If a large CP-violating effect is found in neutrino mixing, it will not directly prove leptogenesis, because the heavy right-handed neutrinos that leptogenesis requires are far too massive to produce at any accelerator, and the specific relationship between low-energy neutrino CP violation and the high-energy leptogenesis mechanism is model-dependent. But it would confirm that the leptonic sector contains substantial CP violation, strengthening the theoretical case for leptogenesis and pointing toward the right class of models. Finding nothing, or finding only a small effect, would not rule out leptogenesis but would constrain the model substantially. The search for the matter-antimatter asymmetry is therefore a distributed, multi-decade, multi-technique scientific program without a single experiment that will definitively answer the question. It is the kind of scientific problem that requires convergent evidence from multiple directions, each experiment constraining the possibilities further until the surviving models can be tested precisely enough to confirm or exclude. It is, in short, exactly the kind of problem that defines the frontier of physics, where the known theory has been exhausted and the unknown territory must be mapped with whatever instruments can be brought to bear. What none of these experiments can tell us, what no experiment can tell us in principle, is whether the answer they find is the answer. Whether the CP violation they measure is the full explanation of why the universe contains matter, or whether it is one piece of a deeper picture that connects to questions about the initial conditions of the universe that experimental physics cannot directly access. We have been using the word nothing very casually, and it is time to be more careful. Because the nothing that the universe might have been instead of something is not as simple a concept as it sounds. In fact, nothing is one of the most contested and philosophically treacherous concepts in all of physics. What is nothing exactly? And is it even possible? The classical intuition is straightforward. Nothing is the absence of everything. No matter, no energy, no space, no time. A perfect void, the kind of nothing that most people imagine when they hear the phrase before the Big Bang. An infinite emptiness, waiting, static, featureless for all eternity, until suddenly something appeared. But modern physics has made this picture untenable. We have already seen that the quantum vacuum is not nothing. Empty space, in the sense of a region containing no particles and no radiation, is still filled with quantum fields that are constantly fluctuating, producing virtual particle pairs, carrying zero-point energy, exerting measurable forces. The quantum vacuum is not a state of nothing. It is a state of something, specifically the lowest energy state of a collection of quantum fields, but a state with real physical properties. The nothing that physics might aspire to is the absence of even the quantum fields themselves. No fields, no vacuum fluctuations, no zero-point energy. A state in which there are no physical laws operating because there are no fields for those laws to govern. This is a more radical form of nothing, and here the philosophical and scientific problems multiply rapidly. Because if there are no physical laws, then there is nothing to prevent something from appearing, but also nothing to cause something to appear. The question of why something rather than nothing presupposes that there's a causal story to tell, that the existence of the universe is the consequence of some prior state or process that could be identified and explained. But if the prior state is genuine absolute nothing, then there is no prior state, no process, no time in which a prior state could exist. The question, why did something appear from nothing, may be grammatically well-formed, but logically incoherent, like asking what is north of the North Pole. Stephen Hawking and James Hartle proposed one of the most serious attempts to address this issue in 1983 with what is called the no-boundary proposal. The proposal uses the formalism of quantum mechanics applied to the entire universe, a framework called quantum cosmology, and suggests that the universe did not have a beginning in the conventional sense, a moment before which there was nothing and after which there was something. Instead, the universe emerged from a state in which time itself was not yet a well-defined dimension. In the mathematics of the proposal, time near the beginning of the universe behaves like a spatial dimension, the boundary between time and space becoming smooth and rounded rather than sharp and singular, the way the surface of a sphere has no edge. There is no first moment of time because time itself dissolves into a different kind of geometry near the origin. In this picture, asking what happened before the Big Bang is not just unanswerable, it is meaningless in the same way that asking what is south of the South Pole is meaningless. The question assumes a structure, time with a boundary that can be approached and crossed, that the physics says does not exist. The universe did not begin. It simply is, in a way that includes its own apparent beginning as a geometric feature of its quantum state rather than as a boundary condition imposed from outside. This is philosophically fascinating, but scientifically incomplete. The no-boundary proposal, while mathematically elegant, has been difficult to work with precisely and has generated ongoing controversy about whether its predictions are well-defined and whether they match observations. The question of the initial state of the universe, of what determined the specific quantum state from which the observable universe emerged, remains open within quantum cosmology. The no-boundary proposal replaces one version of the question with another, more subtle version. It does not eliminate the question. Alexander Vilenkin proposed a related but distinct idea in 1982. Quantum tunneling, the process by which a particle can traverse a potential energy barrier that would be insurmountable in classical physics, is a well-established quantum mechanical phenomenon. Radioactive decay occurs through quantum tunneling. Fusion in the cores of stars is enabled by quantum tunneling at energies below the classical threshold. Vilenkin proposed that the universe itself might have originated through a process analogous to quantum tunneling from a state of literally nothing, not a quantum vacuum with fluctuating fields, but a state with no space, no time, no fields, nothing at all, into a state containing a small, closed, finite universe that then underwent inflation and expanded into everything we see. The mathematics of Vilenkin's proposal is technically developed and genuinely serious, but it faces the same fundamental problem as all such proposals. Quantum tunneling is a process described by physical laws. If there are no physical laws in the prior state, nothing governs the tunneling. The probability of the tunneling event is calculated using quantum mechanical formulas that require a mathematical framework, a Hamiltonian, a wave function, boundary conditions. These mathematical structures are not nothing. They're a form of something. Even if the prior state contains no matter, no energy, no space, and no time, if the calculation requires a mathematical framework, then that framework is a presupposition, not an explanation from nothing. This leads some physicists and philosophers to argue that the question, why is there something rather than nothing, is not a scientific question at all in the conventional sense. Science explains how one thing follows from another, how given certain initial conditions and certain laws, a certain outcome follows. But science presupposes both initial conditions and laws. It cannot explain why there are laws at all, or why the laws are the ones they are rather than some other laws, or why there are initial conditions rather than no initial conditions. These meta-questions about why there is a physical framework at all, why mathematics describes nature, why anything exists at the most fundamental level, may lie permanently outside the domain of scientific explanation as currently conceived. Or they may not. The history of science is a history of questions that were once thought to be permanently beyond reach, being answered by new conceptual frameworks that nobody had imagined. The question of why there is something rather than nothing might be the next such question, waiting for a Copernicus or a Newton or an Einstein to reframe it in terms that make the answer accessible. We cannot know in advance which of these possibilities is correct. There is a class of ideas in modern cosmology and theoretical physics that are genuinely unsettling, not because they are wild speculation, but because they're the logical consequences of theories that have strong empirical support in other domains. These ideas collectively go under the name of the multiverse, though they come in several distinct varieties with different theoretical motivations and different levels of speculative risk. The most conservative version, in the sense of being most directly motivated by established physics, comes from cosmic inflation. The same inflationary mechanism that is believed to have driven the extraordinary expansion of the very early universe and that explains the flatness and uniformity of the observable universe also predicts, in most of its theoretical implementations, that inflation does not end everywhere simultaneously. Different regions of the inflating universe exit inflation at different times, each becoming a separate expanding region with its own properties. Meanwhile, the regions that have not yet exited inflation continue to expand exponentially. The result is an eternally inflating background that continuously spawns new non-inflating regions, each potentially with different physical properties determined by the specific way inflation ended in that region. This is eternal inflation, and it produces what is called the inflationary multiverse, an enormous or possibly infinite collection of distinct universes, each beginning with its own version of the Big Bang, each potentially governed by different physical laws. If the inflationary multiverse is real, then the constants of physics in any given universe, including the degree of CP violation, might vary from universe to universe. Some universes would have too little CP violation to generate any matter-antimatter asymmetry and would be empty of matter. Some would have too much CP violation and might generate an asymmetry so large that the early universe dynamics would be qualitatively different from ours. And some, by a kind of cosmic selection, would have just the right amount of CP violation to generate a matter-dominated universe capable of forming stars, planets, and observers. This is a version of the anthropic argument. We observe a matter-dominated universe with a specific degree of CP violation, not because those values were required by the laws of physics, but because they are the values in a universe where observers can exist to observe them. Most universes in the multiverse might be empty of matter. We find ourselves in one that is not, because the ones that are empty have no observers. The anthropic argument is controversial in a specific and important way. It is not wrong in a simple logical sense. If the multiverse is real and if the constants of physics vary across it, then the anthropic selection effect is real, and it does explain, in a certain sense, why we observe the values we observe. The explanation is selection bias. We are here to ask the question because we are in a universe where the conditions for our existence were met. Most of the time, in most of the multiverse, nobody is asking the question because there is nobody there. The problem with the anthropic argument is that it can feel like the abandonment of explanation rather than its achievement. Science, in its most productive mode, does not explain why something is the case by pointing out that if it were otherwise, nobody would be here to notice. Science explains why something is the case by identifying the mechanism, the law, the initial condition, the process that produced it. If the answer to why is the matter-antimatter asymmetry 1 part in a billion is because that is what our particular bubble universe in the inflationary multiverse happened to get, and the anthropic selection ensured that we live in a bubble where it worked out for matter, then we have explained the observation, but we have not explained the mechanism. To be fair, this critique applies differently depending on what we think counts as explanation. If the multiverse is real and if the constants vary, then the anthropic argument is correct and is in fact a scientific explanation, just not the kind we're used to. The testability problem is more serious. If the other universes in the multiverse are causally disconnected from ours, as eternal inflation implies, we cannot observe them, cannot measure their properties, and cannot in principle confirm or refute the claim that they exist with different physical constants. An explanation that is in principle untestable is uncomfortable territory for physics, though not obviously for reasons that make it wrong. Some physicists argue that the multiverse is not a scientific theory at all for this reason. Others argue that it is scientific because it is the logical consequence of testable theories like inflation and string theory, and that the consequence inherits the empirical credibility of its premises even if the consequence itself cannot be directly tested. This debate is ongoing and unresolved, and it reflects a genuine tension at the frontier of physics between the desire for mechanistic explanation and the mathematical consequences of the best theories we have. What is clear is that the existence of the universe, the fact of something rather than nothing, points toward either new physics within our observable universe that we can find experimentally, or toward a framework of multiple universes that is connected to our observable universe only through theoretical inference, or toward something genuinely unprecedented that neither of these categories captures. These are 3 very different kinds of answers to the same question, and we do not yet know which category the true answer falls into. There is one more layer to the question that has been quietly present throughout this documentary, surfacing occasionally and then submerging, waiting for the right moment. It is the layer that connects the most impersonal of all scientific questions. Why does the universe contain matter at all? To the most personal of all human experiences, the fact of being aware that the question can be asked. Consciousness is not a topic that particle physics usually addresses. The question of why the universe contains something rather than nothing is usually framed as a question about physics, about quarks and antiquarks, and CP violation and baryogenesis. But there's a sense in which the question is ultimately a question about why there are observers at all. Because a universe of matter that contained no minds would be a universe in which the question could never arise. The matter would be there, organized into stars and planets, and perhaps in a complex chemistry, but no one would notice. No one would look up and wonder why. The universe would contain something, but it would contain something in a completely silent and unobserved way. The matter-antimatter asymmetry is the precondition for observers. Without the 1 in a billion excess of matter over antimatter, there are no atoms. Without atoms, there is no chemistry. Without chemistry, there is no biology. Without biology, there is no evolution. Without evolution, there are no minds. Without minds, there is no awareness that a universe exists. The improbable asymmetry that produced the material universe also produced billions of years and many physical and chemical processes later, the beings who can ask why it happened. This is not a mystical statement. It is not an argument for design or purpose. It is a straightforward physical consequence of the matter-antimatter asymmetry. The asymmetry is the causal ancestor of everything that followed. The precise value of 1 in a billion is the specific number that produced the specific density of matter in the observable universe, which produced the specific rate of galaxy formation, which produced the specific stellar populations, which produced the specific abundance of carbon and oxygen and nitrogen through stellar nucleosynthesis, which produced the specific chemistry of life on Earth, which produced, among a great many other things, human beings who build particle accelerators and write equations and ask questions. Whether this chain of causation is itself an explanation for the asymmetry, whether the existence of observers is in some sense the reason for the asymmetry, is the question where physics and philosophy meet most uncomfortably. The strong anthropic principle, in its most extreme formulation, suggests that the universe must have the properties that allow observers to exist because observers are necessary for the universe to exist in any meaningful sense. This is a position that some physicists and philosophers take seriously and that others regard as category confusion, as smuggling teleology, purpose-driven explanation, back into a framework that should be purely causal. Physics does not know what to do with consciousness. The hard problem of consciousness, why physical processes give rise to subjective experience, why there is something it is like to be a brain processing information, why the matter and energy of a universe organized in a particular configuration becomes aware of itself, is as open and as resistant to scientific resolution as the matter-antimatter problem, and arguably more so. The two problems are connected in the sense that both require the physical universe to be exactly as it is. But beyond that connection, they do not illuminate each other. Explaining the origin of matter does not explain the origin of awareness, and vice versa. What can be said with honesty is this. The 1 in a billion excess of matter over antimatter in the first fraction of a second of a universe's history is the deepest root of your own existence. That number is not arbitrary in its effects. Change it by a factor of 2 or 10, and the universe that results looks different in ways that might or might not permit complexity. The number is what it is, encoded in the initial conditions of reality, and everything that has followed from it, including your ability to read these words and find them meaningful, is a consequence of that initial condition having the value it had. Why it had that value is the question. Physics has a horizon, not a physical horizon like the edge of the observable universe, but a conceptual one, a point beyond which the tools of physics, as currently constituted, cannot reach. That horizon is located at a time of approximately 10 to the power of negative 43 seconds after the Big Bang, an interval called the Planck time. Before the Planck time, the temperature and density of the universe were so extreme that quantum gravitational effects would have been dominant. Space and time themselves would have been subject to quantum fluctuations so large that the smooth, continuous space-time of general relativity would have broken down completely. To describe what happened before the Planck time, you would need a theory of quantum gravity, a framework that reconciles general relativity with quantum mechanics. We do not have one. Loop quantum gravity and string theory are candidates, but neither is complete and neither has made confirmed experimental predictions that distinguish it from alternatives. The matter-antimatter asymmetry was generated at times much later than the Planck time. Baryogenesis scenarios typically operate at times of 10 to the negative 30 seconds or later at temperatures well below the Planck energy. So the quantum gravity horizon does not directly block our access to baryogenesis. We do not need quantum gravity to understand the mechanism that generated the asymmetry, assuming it occurred when we think it did. But the initial conditions that determined the universe's properties, including whatever it was that made the early universe favorable for baryogenesis, the specific way the inflaton field was configured, the specific quantum state from which inflation emerged, the specific values of the fundamental constants that determined the degree of CP violation. All of these trace their ancestry to conditions at or before the Planck time. The initial conditions of baryogenesis were set by whatever happened in the Planck era. And the Planck era is beyond our current theoretical reach. This is a precise and honest statement of where the chain of physical explanation currently terminates. We can trace the matter-antimatter asymmetry from the observed universe backward through Big Bang nucleosynthesis, through recombination, through the quark-hadron transition, through the electroweak transition, backward through various baryogenesis windows, backward through reheating after inflation, backward through the inflationary epoch itself. And at some point we arrive at the Planck boundary, and the chain of backward tracing runs out of road. Beyond it is a domain where our current theories are not equipped to operate. Whether a future theory of quantum gravity will allow us to push the explanation further, to say with confidence what the quantum state of the universe was at the Planck time, and why it was that state rather than some other state, is genuinely unknown. It is not obviously impossible. Some proposals for quantum cosmology, including the Hartle-Hawking no-boundary proposal and Vilenkin's tunneling proposal, attempt to address exactly this question by describing the quantum state of the universe at its origin. But these proposals are incomplete, their predictions are uncertain, and the question of what determines the initial quantum state of the universe remains one of the deepest unsolved problems in theoretical physics. The silence of the first moment is not comfortable silence. It is the silence of the frontier. Beyond it lies the answer to the most fundamental question physics can ask. On this side of it, we have extraordinary knowledge, beautiful theories, precise measurements, and one enormous gap. Before we arrive at the final synthesis, it is worth pausing to ask a question that the narrative has so far treated as settled, but that deserves more careful consideration. How confident are we that the universe is truly matter-dominated? Could there be large regions of antimatter somewhere in the observable universe that we have simply not yet mapped? The answer is that we are extremely confident, and the reason reveals something important about the thoroughness of the observational case for the matter-antimatter asymmetry. If large regions of antimatter existed in the observable universe, say an entire galaxy made of antimatter, or an entire galaxy cluster, the boundary between that region and the surrounding matter would be a surface of annihilation. Matter and antimatter meeting at the boundary would annihilate, producing photons at a specific energy, 511 keV, the rest mass energy of an electron and positron converted entirely to gamma radiation. This annihilation boundary would be an extremely bright source of gamma rays at precisely that energy visible to gamma-ray telescopes across enormous distances. No such boundaries have been observed. The gamma-ray sky, surveyed in exquisite detail by the Fermi Gamma-Ray Space Telescope, among other instruments, shows no evidence of such annihilation regions at any scale from our local galactic neighborhood out to cosmological distances. The absence of this signal places an extraordinarily tight constraint on the amount of antimatter that could exist in segregated large-scale structures in the observable universe. The universe is, as far as any observation has ever indicated, uniformly matter-dominated on all scales from atomic nuclei to galaxy superclusters. Small amounts of antimatter do exist in the present universe. Cosmic rays, high-energy particles arriving from outside the solar system, produce antiprotons and positrons when they interact with interstellar gas. These secondary antiparticles are produced in small quantities and annihilate relatively quickly when they encounter ordinary matter. The AMS-02 detector on the International Space Station is measuring the cosmic ray antiparticle spectrum with high precision, searching for excesses above the expected secondary production rate that might indicate primary sources of antimatter, perhaps from dark matter annihilation or from some other exotic process. There are also natural antimatter sources in the human body. Potassium-40, a naturally occurring radioactive isotope present in the body in small amounts, undergoes beta plus decay, emitting positrons. On average, the human body emits roughly 5,000 positrons per second from this source, each of which annihilates with an electron almost immediately, producing a pair of 511 keV gamma rays that escape the body without further interaction. The antimatter inside you is produced continuously and annihilates in fractions of a nanosecond, too short-lived and too dispersed to accumulate. The picture that emerges from all of this is consistent and unambiguous. The observable universe is made almost entirely of matter. Antimatter exists in tiny quantities produced locally by high-energy processes and natural radioactivity, but there are no large-scale deposits of antimatter anywhere that observations can reach. The asymmetry is real, it is global, and its origin is unknown. There's a way of relating to scientific ignorance that is defeatist. We do not know the answer, which means we are failing, which means the project is incomplete, which means something is wrong. This is a misunderstanding of how science works and of what scientific ignorance actually represents. The matter-antimatter asymmetry is not a failure of science. It is science doing exactly what it is supposed to do, which is to push understanding forward until it reaches the genuine limit of the known and to identify precisely where that limit lies. A century ago, we did not know that matter and antimatter existed in any asymmetric relationship. We did not know that the early universe had been hot and dense enough to produce them in large quantities. We did not know what CP violation was, or that it was a feature of the weak force. We did not know that neutrinos had mass or that they oscillated between flavors. We did not know the age of the universe or the composition of its energy content or the existence of the accelerating expansion that dark energy produces. All of that knowledge has been assembled step by painstaking step over the past century of physics and cosmology. The Sakharov conditions were identified. The Standard Model was constructed and tested to extraordinary precision. The CP violation in kaon and B meson decays was measured. The cosmic microwave background was mapped with exquisite detail, establishing the temperature fluctuations that encode the physics of the first 400,000 years of the universe. The matter-antimatter asymmetry was confirmed at the level of 1 part in a billion. The neutrino mass hierarchy is being measured. The CP violating phase in neutrino mixing is being constrained. Each of these steps was an act of genuine discovery, a piece of knowledge that did not exist before and that now exists permanently. The fact that the steps have not yet reached the final answer does not diminish them. It locates them correctly as progress toward an answer that is still ahead. What the question, why is there something rather than nothing, gives us, beyond the specific scientific puzzles it generates, is a sense of scale. Not the scale of size, which the universe provides abundantly, but the scale of depth. How deep can a question go? This question goes all the way down. It goes down through the layers of chemistry and nuclear physics and particle physics and quantum field theory and quantum cosmology and quantum gravity, all the way to the structure of physical law itself, and then past the edge of where physical law can currently speak. It is the question underneath all other questions, the ground level of all inquiry, the point at which asking why leads not to another mechanism, but to silence. That silence is not emptiness. It is the sound of the frontier. And the frontier is where science lives. Let's be honest about where we are. Not the reassuring kind of honest, where we wrap the mystery in elegant language and let the beauty of the open question substitute for the missing answer. The genuinely honest kind, where we look at what we know and what we do not know and refuse to confuse the two. We know the universe contains matter. Every measurement ever made, every atom ever weighed, every spectrum ever taken, every cosmic ray ever detected, every gamma ray ever mapped across the sky confirms this with a precision that is beyond any reasonable doubt. The observable universe, a sphere roughly 93 billion light-years in diameter, containing somewhere between 100 billion and 2 trillion galaxies, each containing hundreds of billions of stars, is made almost entirely of ordinary matter with no significant deposits of antimatter anywhere that observations have ever reached. This is established. This is not contested. We know that matter and antimatter are produced in equal quantities in every particle physics process ever observed in a laboratory. Every accelerator experiment, every cosmic ray interaction studied, every nuclear decay measured produces matter and antimatter in perfectly balanced pairs. The laws of physics, as we observe them operating today, do not create an excess of matter over antimatter. They create them together and they annihilate them together. Equal amounts in, equal amounts out. This is also established and not contested. We know, therefore, that something in the early universe violated this balance. Some process operating in the first fraction of a second of time produced slightly more matter than antimatter, by a ratio of 1 part in a billion, and this excess survived the subsequent annihilation of matter-antimatter pairs to become the material content of the observable universe. This inference is airtight. Given the first two facts, the third follows necessarily. The asymmetry happened. The mechanism remains unknown. We know the three conditions that any successful explanation must satisfy. Sakharov's conditions, formulated in 1967, have stood as the framework for every subsequent theoretical attempt. Baryon number violation, C and CP violation, and departure from thermal equilibrium. These are necessary. They are not sufficient. They define the problem. They do not solve it. We know that the standard model of particle physics, the most precisely tested theory in the history of science, is insufficient to explain the asymmetry. It contains CP violation. It does not contain enough. The gap between the standard model's CP violation and the required amount is enormous. The standard model fails to explain existence. This is not a minor anomaly at the edge of the theory. It is a central, gaping failure at the heart of our most successful physics. We know that several extensions of the standard model could in principle generate the required asymmetry. Electroweak baryogenesis requires a first-order electroweak phase transition and additional sources of CP violation beyond the standard model. Leptogenesis requires heavy right-handed neutrinos with CP violating interactions. Both require physics that has not been observed. Both make predictions that current experiments are working to test. Neither has been confirmed. We know that neutrinos have mass and oscillate between flavors, providing a window into leptonic CP violation that may be measurable in the next generation of experiments. We know that Dune and hyperchemiocandie will measure the CP violating phase in neutrino mixing with high precision within the next decade or two. We know that if that measurement reveals large CP violation in the leptonic sector, it will strengthen the case for leptogenesis substantially. We know that if it reveals small or absent CP violation, it will constrain leptogenesis models significantly. We know that the initial conditions of a universe, the specific quantum state from which everything emerged, the parameters that determine the character of the inflationary epoch and the properties of the universe that emerge from reheating, are not predicted by any current theory. They're inputs, not outputs. Physics, as currently formulated, describes the evolution of the universe from its initial state. It does not explain what determined the initial state. This limitation is not a technical gap waiting to be filled. It may be a fundamental feature of the relationship between physical law and the origin of the universe. We do not know what dark matter is. We do not know what dark energy is. We do not know whether they have any connection to the matter-antimatter asymmetry. We do not know whether the inflationary multiverse is real and whether the constants of physics vary across it. We do not know whether the anthropic argument for the asymmetry is correct or whether it is an evasion of a deeper mechanical explanation. We do not know what happened at or before the Planck time. We do not know whether the question of why there is something rather than nothing has an answer within the framework of physical science or whether it points towards something outside that framework. These are not rhetorical qualifications appended for intellectual humility. They are precise, honest statements of the current state of knowledge. The frontier of understanding is real. It is here. This is it. And now the most important thing to say about all of this. Every atom in your body was produced by the process we have been describing, not metaphorically, not poetically, not as a figure of speech. The specific nuclear physics of the early universe, the specific asymmetry between matter and antimatter, the specific character of the baryogenesis mechanism, whatever it was, produced the protons and neutrons that eventually became, after billions of years of stellar and galactic evolution, the atoms that eventually became the molecules that eventually became the cells that eventually became you. Your existence is the direct physical consequence of that 1 in a billion excess. You are, in a completely literal sense, the surviving fraction. You are the residue. You are what was left when almost everything was canceled. The universe tried to erase itself and came up one part short. You're that part. The question of why you exist, stripped of all its personal and psychological dimensions, and asked at the most fundamental physical level, is the question of why the universe was asymmetric by 1 part in a billion in the first fraction of a second of time. That question is open. It is not going to be answered tomorrow. It may not be answered in your lifetime or in many lifetimes after yours, but is being asked, seriously, rigorously, by thousands of scientists working in accelerators and underground detectors and mountaintop telescopes and in the abstract spaces of theoretical physics. Every measurement, every constraint, every falsified hypothesis, every confirmed prediction is a step toward an answer that is located somewhere ahead in the history of human inquiry. We cannot see it yet, but the path toward it is real and it is being walked. The universe created the conditions for its own examination. It produced, through a chain of physical processes beginning with a 1 in a billion asymmetry, beings capable of asking why the asymmetry existed. Whether that circularity means anything, whether it points towards something deeper about the relationship between observers and the observed universe, is a question that sits at the boundary between physics and philosophy and may sit there permanently. What is clear is this: the universe contains something. It should, by the strictest reading of its own laws, have contained nothing. The gap between what the laws predict and what exists is the gap where you're standing. The question that fills that gap is the deepest question ever asked. And the silence at the bottom of it is not the silence of an answer withheld. It is the silence of a question so large that reality itself has not yet provided a frame large enough to contain the answer. The universe is made of something instead of nothing because something somewhere in the first impossible fraction of a second of time broke the symmetry, tipped the balance, left a remainder. That remainder became everything, and everything eventually learned to wonder why.